the chance to come here to Cambridge. It's been a while since I've been here, and it's a pleasure to be here, even though it's a short visit. But, so what I'm talking about is something I've been working on for many years, and I think there are several people in the audience here that heard various versions of this talk before. And there's one real expert in the audience, Roger. So a lot of this is going to be very close to things Roger has done, Roger Bylowski has done, anyway. Somehow this is part of a general program I have at the moment, which is trying to understand some geometric versions of T-duality. And what I'd really like to get out of it is some metrics of special holonomy. This is going to be the HyperKaehler story, and those who've heard of the HyperKaehler, quaternion-Kaehler correspondence, that fits into the quaternion-Kaehler part of the story. And you can try and do G2 things and things like that, but HyperKaehler is going to be more than enough for today. And probably I'm going to get sidetracked into HyperKaehler in dimension 4, because there are some things to say there, which I ended up sorting out in the process of working on this. So there are two different constructions floating around for what I'm after. A large part of the project is just trying to fit those constructions together. But let me start with the one that's easiest to understand first. And this is what Andrew Dykes and I called HyperKaehler modification. So in this, you start with an arbitrary HyperKaehler manifold M4n, and you want a triholomorphic isometry, which has a moment map as well. So this is tri-Hamiltonian. Let's generate an S1 action. Though a good chunk of what I'm going to say is going to apply to R actions as well, but let's say S1 actions. That will get me out of topological trouble sometimes anyway. So we start with this, and let's take the moment map. Here's the moment map, the HyperKaehler moment. So M is HyperKaehler. Yes. Okay, so what the modification does for you is give you a new HyperKaehler manifold in the same dimension. So this might be 4n-dimensional. The modification is take this M and take a product with R4, 4 to the flat HyperKaehler space, so just with the quaternions, and then take the HyperKaehler quotient by the action of X and the standard diagonal action, or minus the standard diagonal action, is the convention on H. So what do you do to take the HyperKaehler quotient? You take the zero set of the moment map here, and then just divide out by the group action. And here rho is just the difference of the two HyperKaehler moment maps. So this mu H is really conjugation by your point in H, Qi, Q bar, if you set it up. So it's just a quadratic function in the quaternion. But, so that's so the HyperKaehler quotient construction. This always gives you a new HyperKaehler manifold. Getting something smooth out of this is not hard. All you have to do is make sure that X acts free on the zero set of this mu. So this is smooth. If X acts free. Which is exactly the condition that the HyperKaehler quotient of n by X is a smooth manifold as well. It gives you a smooth manifold.
Is X a vector field?
So X is a vector field, yes. Yeah. Generating S1 action. Yeah. Sorry, yes. So this is smooth, and there's several other nice things about this. So
But H doesn't have to generate circle action.
XH generates the standard circle action.
Standard.
So yeah, so XH is I comma minus I on C2. Yeah. So the standard triholomorphic standard action on H. So we get a nice smooth manifold out of this modification. It's complete whenever M is complete. Yeah. It contains a copy of the HyperKaehler quotient of M by X as a fixed point set. Don't know how many. So X is contained in what the modification gets a circle action again. So you can use one of these vector fields to generate it. And I'll just call it X for the moment. So it contains a copy of the HyperKaehler quotient. But this HyperKaehler quotient is now, this is 4 dimensions less than the manifold you started with. So. And there's some nice features in that you can compute, if the topology of this is finite, then so if I assume that the fundamental group is trivial, then the second Betti number of the modification is just the second Betti number of the regional manifold plus 1. There are some people who interpret this as adding a brane to some configuration. It's change your cohomology. But, so there are several nice features about this, but it's making the manifold more complicated. Yeah? It's adding more cohomology to the manifold. Yeah, what's a basic example? So if I take flat R4 and modify that, then what do I get? I get the Iguchi-Hansen metric over on the cotangent bundle of CP1. If I do it again, then I get a two Iguchi-Hansen metric, and you get multi Iguchi-Hansen metrics. You can, instead of starting with R4, you can start with S1 cross R3, and then you get the tau metric. Yeah, mod, yes. Yes, tau nodes are not flat. But you get it out as a modification. So you get nice, well-known metrics in dimension 4, and you can do this in higher dimensions and so on. There are plenty of manifolds to apply to. But as I said, this is making things more complicated. Yeah? We're pushing the topology up. And, what would be nice to know is whether you can go backwards and reduce things.
What happens in the Kaehler case?
In the Kaehler case, so this is this modification is an analog of the Kaehler cut.
Okay.
Yeah. So the nice thing about this is that the image of the moment map on M and on the modification, those images are the same. Whereas but in the Kaehler, yeah, symplectic cut, with symplectic moment maps, for a circle action, they're going to hit the real line, and you throw away the part of the manifold corresponding to values on that line below some value, and you put in the symplectic quotient at that value. Yeah. So this is doing something similar, but the HyperKaehler moment map, this mu H on H, is a nice surjective map. Yeah. So you're getting all of R3, and special things are happening only at one value in R3 at 0. So one thing you might like to know about this is whether you can invert it, whether there's a way to go back, and whether there are other constructions that are more general, taking from HyperKaehler to HyperKaehler in the same dimension when you have a circle. Yes?
I have one more question. So
yeah.
When you do the modification of the quaternions, is that a Kuiper variety, like Kroheimer's construction of
you can, because yes, all of these here are, yeah, when you just do H or HN or something like that, yes, then it's Kuiper variety. Yes, yeah. You can pull those out as examples. So and these come as HyperKaehler toric HyperKaehler manifolds. And well, Roger Belowski has classified all complete HyperKaehler manifolds with a Tn action. So when the manifold has dimension 4n, and if it's finite topology, then they come from quotients of flat plate spaces, and so you can think of them as equivalent varieties in some way. But that's not going to play any role in what I'm saying today. So
I don't think they all come from queer varieties. Some of them, but it's a different.
Or the quotients of them, or some submanifolds of them, are some, yes. But they're very closely related, at least, yes. Yeah. So if you think of a queer variety as some general quotient of flat space, yeah. Okay, yeah. So yeah, the other question is, are there other constructions that do this? Take a HyperKaehler manifold in a given dimension and produce a new one in the same dimension. Yeah. So there's one thing hiding in this picture which gives a hint about that anyway. Maybe I'll put it up here for a moment. But, because I'm going to come back to it later, but at this stage it's not going to play a big role, but it's going to point us in some direction. So I can write down a double fibration picture here. The modification is defined as this quotient here. And let me not worry about niceties, but away from various points, this is essentially a pair of circle bundles. Yeah? There's a double circle fibration. And, well, that's the sort of setup you want when you want to talk about T-duality. And there is a way to move geometry around this picture here. But the naive way to move things around won't give you HyperKaehler metrics if you start with HyperKaehler. So what you can do is look at this picture and get an idea how to do it in general. So it's going to go a while before I start telling you how to do that, because there's one obvious way to generalize this construction here. You can replace the H up here by some other four manifold, HyperKaehler 4 manifold with a circle action. Yeah. So we can generalize. Yeah. So let's replace H by an N4. This should be a complete HyperKaehler 4 manifold. Yeah. With, I better put the word effective in here. Effective triham's action. Circle action. Yeah. So let me call the vector field generating this action xn, and then the moment maps are mu n and so on. Yeah. So yeah, that's something you can do formally, and sometimes it will work and sometimes it won't. But one obvious question turns up when you start writing this down: which manifolds N4 exist? And Roger has the answer when the topology of N4 is finite, so when the second Betti number is a finite number. So, yeah. There's well, there's some other obvious examples, but what I want to show you is that you can actually get the whole list of examples for these manifolds first. Yes.
I mean, you seem to have a circle acting on two manifolds.
Yes.
Defined through two vector fields.
Yes.
But you want it to be consistently one circle action.
So,
isn't there a danger that you go around the circles at different rates or something?
yes. So this is why this is a standard circle action here rather than twice the standard circle action or something like that, and so on. So you want things to be, so this XH has the advantage of being free away from the origin. Yeah. And then you just combine it with this X being free away from the corresponding level set, and you'll get a free action on M. So I'm looking to get free actions to generate manifold quotients rather than orbifold quotients. And of course, there's a lot of what I'm saying that could be modified to talk about orbifold situations. But
I mean, in principle, you've got a torus acting.
I've got a two torus acting, exactly.
But somehow you're choosing a circle in
there. Yeah, so I'm choosing some circle in there. That's giving me the projection down to the right. Yeah. On the other hand, I could choose just the XH to generate one. That's giving me the projection down to the left. So maybe I should have put that on here. Yeah? So xh is here, and this is. So those are two projections, and there are other choices, but they're essentially equivalent when you're asking things to be smooth and so on. So you can flip xh to minus xh, for example.
I guess, okay, but I also have a mixed point again.
Yes.
So xh, well, it's a standard one, so it
Yes.
closes after period 2 pi. But what if the orbit of x closes after irrational?
Ah, sorry. Yeah. So when I say an S1 action, I mean period 2 pi. Yes.
You don't mean
Yeah.
period.
Yeah. Okay. Yes. Was that what you were after?
I'm basically worried about that, yes.
Yeah.
Yes, some compatibility issues.
Yes. I'm thinking there's an action generator which is a genuine map, effective map from S1 to M. Yes. Yeah. Yeah. Standard S1. Yes. So yes. No, I've been through that confusion myself before as well. Good. So yes. So the first question is, can you classify these? What are the examples of these N4s, and can you classify them? And of course, a lot of the people here know the list here and the possibilities. So there's the what does the Gibbons-Hawkins ansatz tell you? So this N for the metric here has the following form. Let me write it this way. Away from fixed points. Yeah? So mu I, mu j, and mu k are the components of my HyperKaehler moment map. And V here is, a little frustratingly, it's 1 over the length of the vector field squared. So this is only making sense away from fixed points, so where the vector field is 0. And beta is a 1 form. It should be squared, yes. And it satisfies this standard monopole equation. So you think of it as a connection 1 form for a circle bundle over an open set in R3, and it satisfies this one-pole equation. So it's equivalent to the HyperKaehler condition. So locally, every 4-dimensional HyperKaehler manifold with free circle symmetry is given by this. And what this equation down here says that V is a harmonic function on R3. So V is initially it's an invariant function, so it descends to the quotient. V is a harmonic function on R3, and if you make different choices of V, then you get different metrics. Yeah? So V is a harmonic function in R3, and you get Uvici-Hansen. So when I set things up, this comes out as 1 over 2 times the normal mu. This is Euclidean distance. Maybe I can move it around, put the center somewhere else, to some p. Or if I want to make this a multi-one, then I can take a sum of these to some finite value k. So I take k distinct points in R3. Yeah.
It's not when you have 1 point you get the flat metric.
If I just have 1 point, then it's with flat metric, yes. And then when I have 2, yes, I get Uvici-Hansen. Sorry. Yeah. Yes, of course. So these PIs are distinct. Yeah. And then there's tab-nut, which comes in multiform as well. And all I have to do is add a positive constant to this Uvici-Hansen. And now I'm going to abuse things. I can let k be 0. In this case, just have a constant potential. That will generate the flat S1 plus R3. So those are the ones that Roger classifies as the finite topology ones. But one thing you can do in these things is let this k go to infinity. Yeah. So you get A infinity metrics. The infinity is just so again, the PIs here have to be distinct, and the only other requirement is that this sum converges at some point of R3. So converging into a single point is actually enough to force convergence away from all the PIs. So that's a consequence of Harnack's principle for harmonic functions. So this just has to converge at some point of R3. So there's the potential there. So 1, and then once it does that, it converges for every q different from pi. And well, you can make a Taubnut version of this, has a Taubnut deformation. Maybe I call it Tn infinity. Yeah. Then the V for this is just a positive constant plus infinite 1. So this list is very well known. I guess these infinite versions were proved to exist by Anderson and Lebrun and Kronheimer mid-90s or a little earlier than that, and Goto has constructed them as infinite dimensional HyperKaehler quotients and things like that. And these always give rise to complete metrics. So whenever you get convergence here, then you get completeness as well. So the Anderson, Lebrun, Kronheimer paper doesn't discuss that very much, but it's not that hard to prove. So not hard to prove if you think about completeness in the right way. So the way to think about completeness in these situations is every time you have a curve that doesn't lie in any compact subset of the manifold, then it has to have infinite length, which is a nice flexible way to think about things with completeness without worrying about geodesics and things like that. So it works well with these fibrations. Well, they're not quite fibrations, they're maps with compact fibers and so on. That quickly gives you proof, so these are always complete metrics. Okay, so my claim is that...
Say that criterion again?
So there are plenty of quantifiers in there. So every time you take a curve on the manifold which doesn't lie in any compact subset, then its length must be infinite. Yeah, guarantees. Yeah. That implies completeness. Yeah, yes, it's equivalent. Yes. So I think there's a version of that that's an exercise in Docamo for surfaces, but I'd forgotten about it, and then there was a paper by Cortez and his co-workers that use this in some context. It's a very useful reminder.
It's the same like saying every curve of finite lengths have some accumulation point.
Yes, yes, yes. That's the same, yes. But thinking in terms of the compact sets actually makes it work quite well here as well. Yeah. Good. So, yes, because I think the Anderson-Kronheimer-Lebrun paper just does this for one particular set of PIs. So this sum is finite somewhere. This implies these PIs have no accumulation point as well. Have no accumulation points in R3. Which is
more than that, I mean, you can't uniformly. I mean,
no, you can't. They can't be uniformly spaced here. So the example I think Kronheim, Anderson, and so on discuss is where the PIs are centered at x0, 0, where x is 1 over I squared. So they have to decay something like that to make it work. So the claim is this is a classification, this list on the right. This classifies. Yeah. So it's the ends satisfying all the conditions up there. So there's always a question with the time here, but so I'd like to say a little bit about how this proof works, and a lot of it works as along the lines of what Roger did, but at the appropriate.
This is only about format. This is now about.
This is just four manifolds, yes.
HyperKaehler formats with circular.
With circle action, yes. Yes.
But somehow you were going to use it.
So I was going to use it to make a general version of the modification construction.
Right, but now we're talking about this. Right?
Yes, so now I'm talking about this for the moment, yes. So these A infinity manifolds, the second better number on these is countable, that's countably infinite. And there's no assumption in this result about behavior at infinity, yes. So about behavior of the metric at infinity. So it just says the list is this, and that's it. So yeah, things are not cylindrical or anything like that at infinity. So so let's sketch some of the things in the proof. And some things I'm going to really sketch a lot, because otherwise the whole talk will end up being on this and I won't get further. But, and a large chunk of this is very close to what Roger has in his setup. So Roger is actually classifying Tn actions on 4n dimensional manifolds. So there are some variations there and some things that simplify here as well. But
it's the four-dimensional case that's essential.
It's the four-dimensional case is essential still in your proof as well, yes. So first you can look at the orbits of the circle action. And there are principal orbits, and then there are some special orbits. And if you look, if you use equivariant tubular neighborhoods and the representations of the circle action and so on, then you quickly find out that every special orbit is just a point. And these points are all isolated. So special orbits are isolated points. So this is also something that's very nice about the four-dimensional case. You don't get any orbits where the stabilizer is a ZK or something like that. And the next thing you can check is that if you take the HyperKaehler moment map, then, well, when the vector field is non-zero, this is automatically a local diffeomorphism. What happens around the fixed points is it becomes a local homeomorphism on the quotient side. So let's take this. Let's just take the quotient. The three-dimensional manifold space that is the quotient of n by x has some singular points. This is a local homeomorphism. So you can check that the action around fixed points is standard. And, get that out from there. And the metric, so this, at least when x is non-zero, you have a Riemannian metric on n. The metric is conformal to R3. That's just what the Gibbons Hawking ansatz is telling us. Yeah? So, so away from this is conformal to flat R3. Yeah? And with harmonic conformal factor. So one of the problems with this is we don't know this moment map is injective. Yeah? So we know it's locally a homomorphism, but there can be covering of all sorts of type. Yeah. So what Roger noticed was that, well, firstly, this harmonic conformal factor, it has isolated singularities, and then there's standard theory for harmonic functions in R3. If you have a positive function with an isolated singularity, then it looks like one of the components in these sums up here with a positive function on top. Yeah? If you want things to come from a circle bundle in the way we have, then the factor actually has to be a +1/2. So there's the Chern class argument there. So, so we know how this behaves with.
If it is subjective.
No, this is a local argument around the singularity. So the factors v and v is has this form around fixed points. Yeah? So it's this plus a harmonic function. Yeah. Okay. So, and then what Roger noticed is this metric, induced metric you get on the quotient here, the smooth part of this quotient. Yeah. This has positive scalar curvature. It's not complete because of the fixed points, but you can move the fixed points off to infinity and still get non-negative scalar curvature. So you can deform Gn on n prime is the thing minus the fixed points, yeah, to complete with scalar curvature non-negative. So that works. That's an essentially gradient in Roger's argument. And now when we have this, then there's a nice result shown in the algorithm, which tells us that the map on n prime has to be injective, and the boundary of the image is what's known as a polar set. So it's a removable set for harmonic functions in R3.
That's a conformal definition.
So this, yes. So we're conformal to a flat metric, yes. Yeah. So this implies that mu, I should be calling it mu bar, I think, on this. So this is injective. And boundary is polar. So there's no difference here to Roger's situation. It's just that we're allowing infinitely many fixed points when we're doing this. But the fixed points are isolated, so there are only countably many with them. So there's no problem there. Okay, so how do you deal with things from here? The tool you need is, let's make sure I'm not jumping over anything, but the tool you need is the Martin representation for positive harmonic functions. So I had a bit of muddle in my notes about what notation I should use for different sets, but because I want this on this set here, so so let's put omega to be the image of this set. Doesn't matter whether I can do this just under the moment map up on the four manifold. It's just that I throw in away the fixed points. Yeah? What I get is that the set of fixed points, we had a local homeomorphism around them, and we know that this map is injective here. The fixed point set is in one-to-one correspondence with the images, so it's injective there as well. So this is a countable set, yeah? And
N superscript x is the fixed point?
it's a fixed point set, sorry, yes. Yeah. If I put this just below n, yeah, then this has boundary some set. The boundary of omega is just the boundary of this f. But potential problem with all this is that this set is discrete. But what you will run into is maybe it has a limit point on the other boundary component, the boundary of omega hat. Yeah. So you need to get away from that. And what I need is the Martin representation. I need the right page in my notes. There's this page here. Yeah, good. So this V now is defined everywhere on this image set, omega, yeah, not the omega hat, the one without the fixed points. Yeah. So V is positive harmonic on omega. And this, then general theory for harmonic functions tells you this has a Martin representation. So I hadn't played with the Martin representation at all until about a year ago. So I don't know how many people know this and how many don't. But, so should I explain? I should explain something about it. Yes?
I don't know anything.
Good. It's a nice machine. It's an old machine as well. It's from the 40s and the 50s. But, so the boundary of this omega, this was a polar set, so it's removable for harmonic functions. So the first thing that tells you is that the Green's functions for omega are just standard Green's functions on R3. So Green's functions. So Green's function for an arbitrary open set in Rn is this standard singular solution to the Laplace equation, and then you subtract off a maximal harmonic function on the whole domain. But anything that's harmonic on all of omega will extend to all of R3, and so be constant. So maximal harmonic and less than this. So what you subtract off is 0. So this is Green's function. Then you write down the Martin kernel. So you choose some base point x0 in your space, and you just look at the ratio of Green's functions at an arbitrary point and x0. So, so we can add a constant to our moment map, so we can assume that 0 is not in F. Yeah? So what do we get if I take, so I choose x0 to be 0, and then this ratio of functions is nothing but y over the x minus y. So this is all nice and concrete. And, the very general theory is very abstract, but this is nice and concrete in this situation. So, and then what does the general theory say? Oh, sorry, that's the Martin kernel. The Martin kernel used to define the Martin boundary of omega. And the Martin boundary of omega is essentially the set of positive harmonic functions you get by letting y go to a boundary point. So a cluster point. Yeah. Omega. And in general, what you need to do here is modulo. You take these. You just look at this set of functions. That's all you need to do. Yeah. So in general, things are a bit complicated. This Martin boundary is often too big, but in this case, this is actually in the case we're looking at with an open set with a polar boundary, this is actually the minimal Martin boundary. We don't have to worry about some technicalities there. And then the Martin representation says,
so this could just be the constant function, or is it?
yes, you can get so if you let the points go to infinity, then you get constant the constant function, yes. And that's definitely useful because that's one of the things we want in our potentials. And the other thing that's going to happen to us are these yi's are going to wander off to a point in the fixed point set. And then it's going to give us the other functions, which are constant over x minus fixed point. So the Martin representation for V, so any positive harmonic function. Yeah. Says, so there is a unique positive measure on the minimal Martin boundary, such that V is given by integrating the Martin kernel. So you have a way to write everything down, yeah? Provided you know what the boundary is, and provided you know what the kernel is, and you know what the measure is. Yeah. So once you've got there, so every positive harmonic function is writable this way. You can generate positive harmonic functions this way as well. So if I take anything that's a Borel subset of delta, then I can generate a positive harmonic function. One nice Borel subset is F. So I just integrate over the set F. Yeah. This is positive harmonic, and it's bounded above by V. Yeah. So we know how V behaves at singular points on F. Yeah. And the general theory tells us that the ratio of Wx over Vx, this goes to 1 on the set F, and it goes to 0 on the rest of the Martin boundary. This is going to force, our concrete form for V is going to force Wx to be essentially the sums I was interested in. Yeah. So, so if you want over 2 norm.
So the 1/2 comes from geometry.
Yeah, the 1/2 comes from the geometry, yes. So if you had all before points, then it'd be different factors. But so this would be x minus q, and we're taking a sum over a fixed point set. Or an integral, however you like to make. So V, so you get this expression is bounded about by V, and V is finite on omega. So this sum converges at some point in R3, and now it converges on the complement of F in R3. And that then tells you that F has no limit points in R3. And now what you can do is go back to Roger's arguments and suppose there are some points here other than the point infinity. Sorry, I forgot to tell you what the full Martin boundary was. There was the point at infinity, and it's the topological boundary of omega in this case when we have a polar. Yeah? So for our case here, this is the topological boundary. So it's just the boundary in S3 rather than R3. Yeah. Yeah. So it's the topological boundary plus an extra point. And now if there was an extra point here, what you can essentially do is find a straight line segment inside omega to a point of this set, which is now conveniently closed, yeah? And calculate the length of that geodesic lifted horizontally to M, and it has finite length, contradicting completeness of N. So N complete implies that the boundary of omega is F, and that tells us that V is this W plus constant. Yeah. So it's a matter of pulling out the right tool from potential theory. I was lucky to find a couple of books that help with that. So the list I write up there is the list of all the 4 manifolds, HyperKaehler 4 manifolds with an effective circle action, which is tri-Hamiltonian. And there are no others. So I can't remember the names of people. People have been looking at the volume growths of these things and things like that recently. There have been a number of preprints coming out and things like that. These are the only possible behavior. Those things are the only possible behaviors when you have a circle symmetry.
So could you just briefly comment on this subjectivity? So there's an issue of whether it's the moment map is subjective.
Is
on
injective.
R3.
Yeah, yes, in the first instance, the issue is whether it's injective. And what we get out of this is something that's not obvious, that it actually is a surjective map.
Yeah,
Yes,
that-
yes, yeah. So that's a corollary, and it's not something we know about other HyperKaehler manifolds with circle action. So
It's naive. I was thinking that some of you've used this given talking, or there could be some other manifolds which weren't in some sense circle bundles over R3, but
right, yes.
were over R2 cross a circle. But I mean,
Yes.
that's not allowed.
That's not allowed here.
It's
Yes,
not
yes,
allowed.
yes, yes, yeah, yes. So it's ruling out a surprising number of things.
Mm.
Yes, I mean, I haven't assumed I was starting with anything simply connected or anything. Indeed, if I could just take the constant function here, then I'm looking at S1 cross R3. You know?
Right.
Yeah, so, and I've assumed nothing about asymptotic behavior at infinity or anything like that. No. So it kills off a lot of questions, which is nice. Yeah, the corollary here is for N4. Yeah, mu is surjective. One of the nice corollaries. Yeah, yeah. Another corollary is that every N4 is essentially a sequence of modifications, maybe an infinite sequence of modifications plus a Taub-Nut deformation of flat space. Yeah. So that's very nice. Nice connection. So that gives me 10 minutes to talk about more general situations. And I can only sketch a few things. Okay, so given N4 like this, yeah, and an N4N as I started with, so HyperKaehler with a tri-Hamiltonian circle action, then I'm going to define a general modification. So I define a general modification. Which is just going to be take the product and then take the quotient, HyperKaehler quotient, diagonal action. Yeah. So one could have done this anyway, but now we know the only things that happen you do with these multi-Ubici-Hatchin or Taub-Nuts or A-infinity metrics and so on. So if you do this in A-infinity metric and make sure X acts freely on the appropriate sets, then so some pre-images of fixed points from Xn, then you're constructing HyperKaehler manifolds with infinite topological type out of this. Okay, so this fits into, away from singularities, it fits into this double fibration picture. So away from singularities. So singularities, I really mean zeros of vector fields. We have a double circle fibration. So let me just put a zero on things just so we're away from this, of these singular sets. Yeah. Okay, so this is double circle fibration. Here is the Xn vector field, which is given the quotient. Let me concentrate on that side first. And I can think about this as a principal bundle. So this is a circle bundle, comes naturally with a connection 1 form, just coming from this
Sorry,
situation.
what was the subscript 0?
So, just keeping away from the fixed points, zeros of vector fields.
Mhm.
Yeah. So I'm not going to have time to worry about those. So this is a principal circle bundle with a connection here. And there's a twist construction, which is a geometric version of T-duality, which tells you how to take geometry from M0 over to whatever space is on the right-hand side in such a picture here. Yeah. So, so what's the data in this construction? M or M0, some general manifold, yeah, with a circle action. So we have an X action acting here. Yeah. There's the curvature of this connection. Yeah. And then there's a moment map relative to these things. So, F could be a degenerate form, but there's something that looks like a moment map. So that's all data over on M, on this side of the picture. This curvature form will essentially tell you how to construct a circle bundle, yeah, with a connection. And once I've got that, then there's a horizontal distribution. It's just the term of theta. And this function A tells us how to lift X. So X prime, which is the thing I want to quotient by here, this is the horizontal lift to H of X, and then there's a principal vector field up here in general. Why would be this Xn? Yeah. And A is how much Y you have to add to it to get something that preserves theta. Yeah. So, and then you put W to be quotient. I called it D0 in this case, haven't I? But it's just a circle bundle in general. So that's a topological picture essentially, and there are some topological things you have to worry about in that picture, but let's not worry about those at the moment. You can put some geometry into this picture because this horizontal space here.
I thought that T-duality usually with a non-trivial first Chern class would give me a germ. So is this really T-duality?
It's my way of understanding what Gary Gibbons and Stella and Papadopoulos did many years ago, and where they said, by T-duality we get, and I can get what they get. So it's my own geometric version of it. So it's not a physics T-duality, but it's producing but it's producing things that look like them when you look at it in the right way. So what's the geometry here? So this horizontal space here, if I use the two projections here, then it's just copies of the tangent spaces on both sides. Yeah. So any tensor we have, we can just, on M, we can just move it up to H, as long as it's an invariant tensor, and then we can push it down. So we use this to move invariant tensors N to what I call H-related invariant tensors on W. And it's a concrete situation, so you can do all calculations and so on. So you can do this for torus actions, and things change quite a bit in the and the general picture there is the same, but what I'm about to say changes quite a bit. So you can move various things through this picture. So you can take a complex structure, and the condition that you get a complex structure out of the other side is that the curvature F here is type 1, 1. So I goes to IW, and so the integral, if you know that F is a 114. So if I was integral to start with. So that's easy to spot. Exterior derivatives behave in a strange way. So if you take an N form, yeah, here, then the d of alpha w, what does this correspond to? So this picture is easily inverted. So this corresponds to taking d of alpha and then correcting by something. So you increase the degree by 2 by measuring this curvature f on, and then you reduce the degree by 1 by contracting with x, which is sort of a strange thing, but everything's set up so the square of this operator is 0. And that's very bad for symplectic structures. It's not good at preserving symplectic structures. So if alpha is symplectic, this term disappears, but this is going to be a non-zero one form whenever x is non-zero. Yes. But if f is decently decently non-degenerate or something like that, you're never going to get a symplectic structure out. So how on earth do we get the HyperKaehler modifications and their generalizations out of this? Well, the complex structures are no problem. But structure. Yeah. So general HyperKaehler modification is replace Gm, metric on M, by, let's call it G tilde M. So what do? I take the original metric and I add on, this is the function we have on N describing the four manifold. On N, it's a function of the HyperKaehler moment map on N, mu I, mu j, mu k. Apply this function to the HyperKaehler moment map on M, yeah? And then multiply it onto the quaternion metric we get by dualizing x. So take the metric in the direction x and take the quaternion expander of that and just scale in that direction. So this is a bit like performing a conformal scaling, but only in one factor. So the general HyperKaehler modification is given by that, and you can think of this as an example of a general modification, a deformation of the original metric. So what you can do generally is throw in a function here.
Guaranteed to be HyperKaehler.
So yes, this is guaranteed to be HyperKaehler, yes. But you can throw in a function here and a function here, and check the only way you get HyperKaehler metric out is if this function is a constant, so you can take it b1, and this function is a harmonic function of the moment map, but not necessarily positive. So there's a general version where you can replace this by something non-positive. So the short story at this point is you can now invert the modification construction just by flipping the sign here. So you can go backwards. And there's a more complicated story about what happens around singularities. And a number of the singularities are essentially forced to look like what happens in the modification constructions. So by taking this very general thing and putting it through this general construction, the only essentially, well, a good number of the possibilities you get to come from this modification construction. So I've used my time anyway, haven't I? We need to have a break before the next talk at least. So, I'll stop here.
Questions? Are you saying now that if you start with a foreign manifold with a circle action, you can lower the betting?
Hopefully. So one condition to do this is that you need a fixed point set that is codimension 4, which is already a big condition for your circle action. And no, I don't have all details in place, but it looks like in that situation, I'm very close to being able to say it. But there's at least a catch. If you look at R4, then the origin is a fixed point set of codimension 4. And R4 is not the modification of anything.
It's not modification.
It's not the modification of any metric.
I thought you
But
said
if
you can reverse it though.
Yes, but so there's you can flip the sign here, but do get something positive definite. Yeah. But with R4, you can make a tab nut deformation, and then it is a modification of something. So I'm 98% certain at the moment that
But then the nut modification can be also reversed.
well, when you've unmodified the Taub nut, you've got S1 cross R3, which is flat. Yes. Yes. Yeah. So I'm 98% certain this is what's the sort of thing that's happening in the general situation as well. But you need to analyze a bit more about what's happening with the moment map and how the length of the vector field is behaving in relation to that. And there are nasty things about various fibers being non-compact and things like that. It's not quite clear I can control it. There are all sorts of potential things that go wrong when I have no counterexamples. And then I can say a lot of things that point in the right direction. So,
I have a name for you if you're thinking of applying for grants, the HyperKaehler minimal program. Minimal models.
Yes. Yes.
Yeah.
Yes.
I think you alluded to this, but very briefly, could you just clarify? When you had this construction of 4 manifolds
Yes.
with your complete list,
Yes.
classified by these points,
Yes.
if you do the modification,
Yes.
can you either add one point where you like,
Yes.
or subtract one of them,
Yes.
where any one of them?
Yes, you can. That's no
Through
problem.
this
Yes.
Taub
Yes.
nut, through one Taub
So,
nut or something?
no, the Taub nut is adding in a constant overall. But the modification is just putting in one extra point or removing it. And that's not going to ruin any convergence properties at all. So,
Well, how do you
so-
add the 1 point?
so
don't choose
so
one.
the potentials with these things are
Well, the
these,
first construction.
these sums here, weren't they? Yeah, with a finite or infinite sum. You just find an extra p to add to this list and sum, or throw one away. And that's
In
not.
terms of the modification, was that the first construction? We're just using
Yes,
H?
you're just using h is corresponds to
That
that one.
introduced 1 point.
that
There was
introduces 1 point,
in
yes,
that
yes,
discussion, wasn't
yes.
there? There was an origin.
There's the origin and there's nothing else. Yes, that's exactly that. Yeah, yes. I should have made that clearer. Yes.
But if
That's
you want to remove it,
Yes.
how do you?
Well, in the potential here, you just throw one of these terms away.
But what in? Okay.
Or, yes, if I want to remove it then away from the fixed point sets, then it's this double circle model picture. And over the fixed point sets, it's interesting because you've got this horizontal distribution away from the image of the fixed point set. And the whole fiber over the 0 set is what becomes a subset of the original manifold. So it becomes a circle in the original manifold. And that's what has to happen in the other general cases as well. So, and it's frustrating writing it down in certain coordinates, so you have things that look singular, and they're not as singular as they might be.